Okay, so welcome to the mathematics class, and now we are going to learn about the number system. So let's see the topics to be taught here. We'll learn about the introduction to number system, then learn about the rational numbers, then the irrational numbers, then we'll talk about the real numbers and their decimal expansions. And then we'll talk about the representing real numbers on the number line, then operations on real numbers, and then finally laws of exponents for real numbers. So let's start off with our first topic in the list, introduction. So let's have an introduction to the number line. Now many of you have seen number line in your earlier classes, but as you know, number line is a line where equal divisions have been made to represent certain numbers on the line, right? But as given in the figure here, you have learned till now that only integers or whole numbers can be represented on the number line, positive integers as well as negative integers, right? But are these the only numbers which can be represented on the number line? Actually, the number line is continuous. So the answer to this question is obviously no. There are many numbers lying in between any given two numbers. As you can see in the figure here, between number 1 and number 2 we have infinitely many numbers in the form of decimals, and there are different types of numbers. Okay, like say for example 1.5. 1.5 is a number which is in between 1 and 2, right? And it can be represented on the number line. And even further, if you go on dividing it, you can also represent very minute numbers also, like 1.7352. You can also represent such numbers in a number line, and these numbers lie between two integers, as you can see, right? There are two classes of these numbers as written here. The first class is called the rational numbers, and the second class is called the irrational numbers. And in the coming slides we are going to talk about these two types, rational and irrational numbers. So let's start off with rational numbers. Now, what are rational numbers? The definition states, numbers written in the form of p by q or in the form numerator divided by denominator are called rational numbers. But there are certain conditions to it. The first condition is p and q are co-prime, which means there should not be any common factors between p and q. The only common factors between p and q must be 1, right? This is the meaning of being co-prime. And the second condition here is q should not be equal to 0. Okay, because if by chance the denominator becomes 0, the number would not be possible to represent on the number line, because division by 0 is not possible. Okay, like here you can see the examples are there in numbers in the form p by q, 1 by 2, right? And there are also improper fractions, 14 by 5, and we have integers also in the set of rational numbers. Why? Because for 2 we can write 2 as in the fraction form as 2 divided by 1, right? So this is in the form p by q, which where q is not equal to 0, which is here is equal to 1, so we can call 2 a rational number, right? Now for minus 56, like for any negative number, it is the same thing. We can represent minus 56 as minus 56 divided by 1, right? That means this number is in the form p by q, and thus it can also be called as rational numbers. Negative fractions can also be called rational numbers, as I have told you. Numerator divided by denominator, right? And also certain decimals are there which keeps on repeating itself, like here 5.363636 and so on. It keeps on repeating, it never ends. Now these are also called rational numbers, and in coming slides we will show you how to tell whether this is a rational number or not. Now for time being, just remember, when numbers have repeating decimals or the decimals terminate at a particular point, like suppose the number was 5.36 only, then we can tell that the number is rational, right? So here the numbers are rational when written in the form p by q, and p and q must be co-prime, or they should not have any common factors, and q should not be equal to 0, and then only we can call them a rational number. Just 3 points you have to remember for rational numbers, and then we can start off with the irrational numbers. Now irrational numbers cannot be written in the form of p by q, right? Where p and q are integers, p and q must be integers to be represented in the form p by q. It is obvious, because if we are representing a number in the form p by q, p cannot be a fraction, right? If p is itself a fraction, there is no sense of representing a number in the form fraction by fraction or fraction by an integer, right? So irrational numbers are those which cannot be represented in the form p by q, where p and q are integers. And the same thing applies here. If q is 0, then it won't be possible to represent in the form p by q, right? That means irrational numbers are those which can't be written in the form p by q, where p and q are integers and co-prime and q not equal to 0, right? They can be represented only and only by their original forms. Like here, square root of 2, we don't know what is the value of square root of 2, like, right, in the form of integers or in the form of fractions, right? You can put square root of 2 in your calculator to find out a value. It will give a very large value where the decimals are not repeated, they are going at a random fashion, okay? And the same is the case with square root of 5, right? Now square root of 4 is not an irrational number. Why? Because square root of 4 we can write as 2, right? Because 2 times 2 is 4, okay? And as we have told, 2 is a rational number, and if the right hand side of equality is rational number, the left hand side of the equality must also be a rational number, right? So the numbers which cannot for which square roots cannot be found out are obviously irrational numbers, as we don't know their fractional forms or integer forms, right? And this number, as you can see, a very large decimal number where the decimal digits are not repeated, they are just going at a random fashion, as you can see, 1 0 1 2 5 3 1 9 7 and so on, whatever can be the value. So these kind of numbers, non-repeating decimals, are classed in irrational numbers, right? And both the rational numbers and the irrational numbers can be represented in the number line, right? We know how to represent rational numbers in the number line, right? And irrational numbers can also be represented on the number line by a certain technique which we will show in coming slides, right? Now let's see how to represent irrational numbers on the number line. Okay, so we are going to use the famous Pythagoras theorem. So how do we do it? We know by Pythagoras theorem, if a triangle is there with right angle here, whose base is 1 and height is also 1, then the hypotenuse must be square root of sum of the squares of both the sides, right? 1 square, which is 1, plus 1 square, 1 again. So we get the result as the length of the side as square root of 2, right? So we can take this measure, take the measure of square root of 2 and then plot it on the straight line, on the number line, right? And this P point represents square root of 2, right? So what did we do? First, by Pythagoras theorem, we found out the length of the hypotenuse of this right angle triangle, which has length of base as 1, length of base as 1, and length of hypotenuse, length of the perpendicular height also as 1. So we get the hypotenuse as square root of 2, and then we take the same length on the number line to get the plot of square root of 2, and you will find that the position of square root of 2 will lie between 1 and 2, right? And when you put square root of 2 in your calculator, you will find the value to be 1.414 and so on, right? That means the value lies between 1 and 2, which is correct. So by this method we can go on representing numbers on a number line, all the rationals, all the irrational numbers. As you can see, to represent square root of 2 we have used base 1, height 1. Now what should we do to represent square root of 3? For square root of 3, what we should get? We should get square root of 2 plus 1, right? For getting 2 plus 1, we know that this square is 1 square is 1, but which number when squared gives 2? The only number is square root of 2, right? The only number is square root of 2, which when squared gives us the number 2. So we can use square root of 2 as the base and 1 as the perpendicular height to get the hypotenuse of this triangle as square root of 3, right? And then we do the same method. We take this length square root of 3 and then measure and then plot it on the straight line, right? We plot the same length. You may use a compass or a scale and then draw the same length on the straight line, correct? Then for square root of 4 we continue in the same method. Take square root of 3 as the base here and take the height as 1, and you will get the hypotenuse as square root of 4, which is 2 itself, right? So you can plot 2 on the number line. Suppose the number line is here. Let's draw the number line for easiness. Okay, suppose this is the number line. So you can take the measure straight away from here using a compass and then plot it directly here, which will give you the value 2, right? And in a similar fashion we can move on to get square root of 5, square root of 6, square root of 7, square root of 8, and so on, right? That means what we are doing here, we are taking the previous square root as the base and 1 as the height, and then measuring the length of the hypotenuse to get the measure of the irrational number. And what we are doing, we are taking the 0 point as the center and then with the help of a compass drawing a circle which cuts the straight line at certain point here, right? So here we get the value of square root of 5, right? And why is this true? Because if we draw a circle taking 0 as the center and the radius as the length of the irrational number, which we are going to find out, when we take the measure on the number line, the length of the radius is always constant, which is square root of 5, right? And wherever it cuts the number line, we should get square root of 5 there itself. And here, as you can see, the method is shown more clearly. We get square root of 2 at this point, and then we take square root of 2 as the base, and then we get the hypotenuse as square root of 3 by taking the height as 1, and we again plot it on the number line, and then we take the base as square root of 3 and get square root of 4, right? It should be 2, right? Root 5 is somewhere else. Root 5 is far beyond. Okay, so we are done with how to represent irrational numbers on the number line. Now let's talk about the topic real numbers and their decimal expansions. Now what are real numbers? First of all, the set of all the rational numbers and the set of all the irrational numbers together constitute the whole set of real numbers. And why do we call them real? We call them real because we can plot them on the number line correctly, right? We can plot them on the number line. That's why we are called therefore call them the real numbers. That means which really exist, right? Like you can define natural numbers as the numbers which we can naturally count, right? The definition is kind of same here. Real numbers are those which really exist in mathematics. So let's find the decimal expansion of these three given rational numbers: 10 by 3, 7 by 8 and 1 by 7. Let's start off with 10 by 3. Okay, so what do we do to get the decimal expansion? We divide 10 with 3. So first you can see it goes by 3, and here we get 3 3s are 9. We get the remainder as 1, right? Now what do? We add a decimal point here, right? We add a decimal point here. Let me show you separately, right? We divide 10 by 3. So what do we get here? First we get 1, right? We get 9 here. So when we subtract it, we get the remainder as 1. Now as it can't be divided further, so what do? Okay, so here it will be 3, right? It's a mistake. Okay, so we have a decimal point here. We give decimal point here, and what do? We bring a 0 down here. Okay, so here again it can be divided by 3, right? So what do? We take here 3 again. 3 3s are 9, right? So we get remainder 1 again, right? But we have already put a decimal point here, so we can again bring 1 0, right? Then again we can divide with 3. 3 3s are 9, and this process goes on and on, right? You can see it is going on and on. Every time we get the remainder as 1, every time 1, right? So what is happening here? We are going on dividing a number until and unless we get a remainder 0. Okay, and how we are going on with this step? We are adding a decimal point and bringing 1 0 after the remainder of the main division. This portion we divide it mainly, right? And whatever remainder is left after the main division or the integer division, we try to divide them even further by adding a decimal point and bringing down a 0 beside the number, right? And this number 3.33333, as it goes on, we can represent it in a shorter form. And how is that? We can represent the number like this: 3 decimal 3 with a bar above it. And what does this bar tell us? This bar tells us that this number 3 has been repeated over and over again. For example, if we tell it is 5.25 and it has a bar 25 above. Okay, so how can we represent this number in an expanded form? We can write 5.25, 25 again, and 25 again, right? And so on, right? That means the number on which the bar has been put is repeated over and over again. Suppose we take 5.25 once more, but in this case we give bar only on the number 5. So what do we get as the expression? We get 5.2. Now the number 5 has been repeated over and over again. So what is happening here? We write number 5, 5 again, 5 again, and so on, right? That means the number is so long, 5.255555, that we can't represent it on a single sheet. So what do? We just make it shorten and represent the number like this with a bar above the numbers which are being repeated over and over again. So let's recap this once more. You can see the division method. First we do the main division. When we get a remainder, then we put a decimal at the quotient and then bring down a 0 at the remainder, and then we again carry out further divisions. Okay, then gradually, until and unless we get the remainder as 0, we keep on doing divisions. Okay, and we need to put the decimal point only once to bring down a 0. If the decimal point is already put, we can bring down as many zeros as we want in every step, and for each step we can only bring only 1 0, right? Now let's talk about the decimal expansion of 7 divided by 8. Okay, now you can see how this goes on. First we do the main division as usual. It is 7 0, it is 8 zeros are 0, right? Because 7 is lesser than 8. So what do? Here it is not shown the division with 0 because it is obvious that we have to divide it by 0 at first to do the main division. Now what do? We give a decimal point here as shown and then bring down a 0 beside 7. Now the number has become 70. So what do? We write 8 8 is 64 and then carry out division for which we get the remainder as 6, right? As there is decimal point and we haven't got 0 in the remainder yet, we can still bring down one more 0 beside the remainder. So the new number again becomes 60, right? Now we can divide 60 with 8. How? 8 sevens are 56, the nearest number, and ultimately we get the remainder as 4. Okay, so still we have not got the remainder as 0, so we can continue the division further. So what do? As we have a decimal point here, we bring down one more 0 here. Okay, so we can divide again. 8 5 is 40, and yes, at this step we have got the remainder as 0 and our division is complete. Okay, you can say the decimal has terminated, right? You can say the decimal has terminated. You can see the set of remainders as we gradually go on dividing. First remainder has been 6. First remainder was 6. The second remainder was 4, and the final remainder was 0, where we stop our division process, right? That means we can write 7 by 8 in decimal expansion as 0.875, right? And you can see 7 by 8 must be less than 1, right? It must lie between 0 and 1 as it is a fraction. It is a proper fraction, right? So you can see in the decimal expansion it is 0.875, right? So it is obviously less than 1. 0.8 is obviously less than 1, right? So this kind of decimals which at a point, after a point, gets ended up, means we get a 0 in the remainder when we divide. This kind of decimals are termed as terminating decimal. Now in the previous example we have seen a decimal which keeps on repeating itself, right? This kind of decimal expansions are called non-terminating repeating decimals, as they never terminate and they keep on repeating one after the other, right? Now let's take another example of this non-terminating repeating decimal with the fraction 1/7. Now let's find out what is the decimal expansion of it, right? So it is a long process, as you can see. First, as 1 is less than 7, we divide it by 0 and we get the remainder 1 itself. So it is not shown in the figure. We get the remainder 1, right? So we put a decimal point here after 0 and we bring down a 0 here. So the number has now become 10. So what do we do? 7 ones are 7 and the first remainder we get as 3. Okay. So still we have not got 0. So what do? We have the decimal point here. That's why we can bring one more 0 down here, right? So the number has now become 30 and we can carry out the division process. So nearest number, say 4 sevens are 28 and we get the remainder as 2, right? Now still we have not got 0. So as we have decimal point here, we bring down one more 0 here, right? So the number has become 20 and again we can carry out the division process. So 7 to the 14, the nearest number, and we get 6 as the remainder here, and again we have not got 0, so we should continue the process. So you can see till now we have not got any repetition yet, right? So the nearest number 8 sevens are 56, which gives us the remainder 4. Still it is not 0 and we have not got any repetitions of number. So we should carry out the division further, as we have the decimal here, so we can bring down a 0 here. Okay. Now the nearest number 7 fives are 35 and which gives the remainder as 5, right? And still we have not got 0, so we should continue with the division process. In the same process we bring down 1 0 after 5 and then we divide 7 sevens are 49 and we get the remainder 1, which is the same as the number with which we had started, right? That means the same procedure is going to be followed after this step, right? Because there is decimal, we will bring a 0 here, it will become 10, right? It will become 10 and we can carry out the process, and the process will look similar like this, whatever is going on here, right? The process will again repeat itself. That means this set of numbers 1 4 2 8 5 7 is going to be repeated over and over again. This set of numbers 1 4 2 8 5 7 1 4 2 8 5 7 is going to be repeated over and over again if we continue the division process, right? In other words, we can represent it in this fashion: 0.142857 with a bar above it, because this set 142857 is getting repeated over and over again. So I think you have got the process till now. After the normal division process, whatever remainder we get, if we don't get the remainder as 0, we put a decimal in the quotient and then we bring a 0 down beside the remainder, and we divide the new number with the quotient with the divisor, right? Then we carry on the process further. Like if we get a remainder after that, still we can bring down one more 0 beside that number, and the new number can be again divided with the divisor to get 0 in further processes, right? These are the steps we should follow in finding out the decimal expansion of any fraction given in the form p by q, right? And for mixed fraction, what you should do, for mixed fraction you should first convert the number into an improper fraction, then you can carry out the same process as we talked about here, right? So suppose the number given to you is 5.36 with a bar above it, right? 5.36, 36, 36, 36, and it goes on. Now how will you convert this number into a fraction, right? We can convert 5.36 into a fraction directly. How? First we will write it is 5.36, the given number, right? Suppose we are given the number 5.36, no number is repeating, so we can directly find out the fraction corresponding to this one. We should write 536, removing the decimal, and while removing the decimal we should write here 1 followed by the number of zeros, same as the number of places after decimal. Here, as we have 2 places after the decimal, we have written 2 zeros after 1 in the denominator, right? So we can just simplify this fraction further. We can just cancel this and bring it to the lowest term, and at that point we should call it a rational number, right? This number is still not a rational number, right? For being a rational number, our criteria was the numerator and the denominator should have common factor only 1, right? They should be co-prime, or they should not have any other common factor in between them. So we should cancel these 2 numbers and bring it to the lowest form to make it to a rational number, right? So this was quite easy, as no numbers were repeating, right? But if the numbers repeat, what to do? As we do in all kinds of algebra, let what we don't know, let it be as x, right? Let x be the fraction equivalent of this number 5.36363636. Let x be the fractional equivalent of this big number. Okay, so let's multiply it with 100. Why? Because there are 2 decimal places being repeated one after the other, right? So if we multiply it by 100, the 2 decimal places get shift backwards, right? They get shifted to the right, and we get the number as given here, 536 point, and again it follows 363636, right? So what are we doing? We are trying to keep the points, the numbers after the decimal point same in both the cases, right? And we will see why we are doing this. Now what we do, we have the number 100x, we have the number 100x equal to 5.3636 and so on, right? And we have x equals, no, I think it should be 100x equals 536, right? Because we have multiplied it with 100. It should be 536.3636 and so on. And we have x equals 5.3636 and so on, right? Now what do? We subtract these 2 numbers. Now when we subtract x from 100x, so what we get? We get 99x, right? We are subtracting 1x from hundreds of x's, so we get 99x. But the interesting thing is, what do we get here? You can see, if we do subtraction column wise, You can see this 6 gets cancelled out with this 6, so we get 0 here. 3 gets cancelled out with this 3, so we again get 0 here, and we get 0 for this 6 also, we get 0 for this 3 also. Now comes the decimal. 6 minus 5 we get as 1. We can put 3 as it is because there is no number here. 3 and 5, right? So what have we got? 99x as given here. 99x is equal to 531. So what happens here, you can see all the repeating numbers after decimal point has been eliminated. They are just vanished, right? Because of this simple subtraction. Now you can understand why we multiplied the number with 100, right? If the number had been 5.3 with a bar on it, we would have multiplied it with 10, because if we had multiplied with only 10, the numbers after decimal point would still be in a repeated fashion, right? It would be 53.33333 and so on. As the number of places after decimal is 2, which are being repeated, what we do, we multiplied with 100 or 1 followed by 2 zeros, right? And we can get the numbers after decimal points the same. And when we subtract the two numbers, what do we get? We get a number with no decimal parts, right? We get a pure integer. Now you can write x in this fashion. You can divide both sides with 99, and finally you get the result as 531 divided by 99. But remember, it is still not a rational number. For rational numbers, we need to have the numerator and denominator co-prime, or they should not have any common factors. So we cancel them, divide them until we have a number whose numerator and denominator are co-prime, or there are no common factors between them, right? You can see the number has been simplified to 59 divided by 11, which has no common factors between them other than 1, right? You can check it easily. So you can let's revise once again. What do we do? If the number is a repeating fraction, we first find out the number of digits after decimal points which are being repeated, right? Then we try to multiply with such a number like 1 with sufficient number of zeros so that the number after decimal point remains the same as we had in the original fraction, so that when we subtract the two numbers, the decimal part gets vanished. Okay, so this is how we get a fraction out of a repeating decimal. And you can also see why a repeating decimal can be termed as a rational number. It can be represented in form of fraction, right? We have just shown it. So I think you have used pi, the value of pi, quite often as 22 by 7, right? Now if you place pi in your calculator, you will find the value is not exactly 22 by 7. Actually, pi is an irrational number whose value is just huge. Like you can see here, 3.1415926, and it just goes on and on without following any pattern, right? So this pi, we can term it as irrational number, as the decimals which are given here does not repeat itself, right? Now we have used the value 22 by 7 as an approximate value. You can check it by putting in your calculator 22 by 7. You will get the first 5 to 6 places of this decimals may match, but after that it will not. It is just an approximation, right? Hence you can correctly say that pi is never ever equal to 22 by 7. 22 by 7 is just an approximate value of pi. Okay, this is an important fact you should know. Now suppose you were given two numbers, okay, and you were asked tell me any irrational number in between them. Now suppose I ask you, you know the irrational numbers between 1 and 2, right? It is square root of 2. Suppose I give you, tell me an irrational number between 7 and 8. Now should you go and calculate for every step that for every triangle we will apply that Pythagoras theorem and find out which are the irrational numbers? No, there is still an easy method. Suppose we have the two numbers, we are given two difficult numbers like 1 by 7 and 1 by 3, and we are asked, okay, find out the irrational numbers in between these two numbers. So what do we do? First we write the decimal representation of these two numbers, right? Here you can see we have written the decimal representation of 1 by 7 as we have found it in the earlier slides. It is 0.142857, and this 142857 gets repeated over and over again, and 1 by 7, that's why is a rational number. And 1 by 3 has also been written in this fashion, same fashion, where the number is 0.33333 and it goes on, right? Now you can just wildly guess an irrational number in between these two numbers. You can see the first two numbers are 0.14, right? And here the number is 3. So the number should be approximately 0.2, right? If the number is 0.2, it must be between 0.1 and 0.3, right? So we can just randomly guess the number. It should be 0.2. Up to this it is fixed, right? Up to this we have fixed, and then we just keep on putting random values, right? I have put here 0.2, after that 5, 6, 4, 1, 2, 8, 9. You can put any value you wish until the value lies between the given two numbers. Suppose here in place of 0.3, if some number would have been there, suppose 0.2 bar. Suppose the number was 0.2 bar. So I should have chosen a number between 0.1 and 0.2, right? Now if the number between 0.1 and 0.2 I had chosen to be 0.15, it would be greater than this one, right? 0.14. But if I had chosen the number 0.13, it is still between 0.1 and 0.2, right? But the number is lesser than the least number given here. The least number given here is 0.14, right? So you should choose and put random values according to the values given in the question, and you should keep in mind that your number should lie between the given two numbers. Like if my second number, forget this value, if my second number had been 0.2 bar and my first number was this itself, so I should have taken 0.15 and should check at every step whether this number is lying between 0.14 and 0.2 or not. Now I should keep a random number. Suppose I keep 6. Is the number lying between 0.14142 and 0.222? Yes, it is. It is lying between 0.142 and 0.222, right? And then we keep another number. Suppose let's say 4. Okay. So what do? We take the value randomly as 4 and then just check it with the given number 0.14285. Is that lying between 0.14285 and 0.222? Yes, it is. So just keep on adding random values. Suppose this is 2, 1 and so on. So getting irrational numbers in between two numbers is very easy, right? Just keep in mind that the number you are finding out should lie between the upper limit of the numbers given and the lower limit of the number given. Now let's see how to represent this peculiar numbers which gets repeated one after the other on the number line. As they are getting repeated one after the other, we can't actually specify exactly where the value is going to be until and unless we find the fractional view of it and then represent in a number line in the form of a fraction, right? But if you are asked to represent this number 5.37 bar directly on the number line, how will you do it? Here we have a representation of the number line. Now which portion do we need? We need the portion between 5 and 6, right? 5.37 bar lies between 5 and 6. So we take this portion 5 and 6, and what do? We just zoom it out. Okay, we just zoom into it, and here are the set of values we get between 5 and 6. You can see this region has been zoomed in. Okay, so we get different values here. If we space them equally, we get values at regular intervals, like you can see here 5.05, 5.1, 5.15, 5.2 and so on, right? So we have to choose first where does 5.37 lies. You can see 5.37 lies between 5.35 and 5.4 line. It is somewhere in this region. So what do? We again zoom in this region, 5.35 and 5.4. We again zoom in this region and we again divide it equally. Okay, so here what do we get? Here it is 5.37. If you just keep on measuring it and counting it, here we get 5.37. Then after 3 points we get 5.38 and so on, as long as they are equally divided. And here you can see there are much minute values like 5.3725, 5.3750, 5.3775, and the number which we have is 5.3777 and so on, right? That means it should lie between 5.3775 and 5.38, right? It should lie in between this, right? And you can again zoom in and again divide it into further steps, right? And you can keep on doing this. But if you want an approximate location, you can just stop at this step and just mark it somewhere. It is located here, right? Somewhere it is located here. So this point you can call it 5.37777, like this. Okay, at this point the value is 5.37 bar. And how can we tell that this is the value? It is an approximate place, right? The number lies between our shown two numbers, 5.3775 and 5.38. 5.37 bar is obviously less than 5.38, right? And the number is obviously greater than 5.3775. So we can get an approximate value like this. So let's repeat the steps once more. So what have we seen? For representing these real numbers with repeating decimals, first we zoom in to the portion of the number line where we are interested in. Okay, after we zoom in, we still further find out in which division does the number lie. When we find the division or the gap, we again zoom into it, right? And we keep on continuing this process until and unless we are satisfied with the point, with the location of the point which we have to plot, right? Here I have shown you 3 steps. You can be more precise if you keep on following further steps. Okay, the more number of steps you go, the more precise your answer would be. But as the number has been repeating itself infinite number of times, we don't know how many number of times, so you will evidently never get to a correct representation of this number, of this repeating decimal, if you want to plot the number directly on the number line, right? Thank you.